Awesome. Again, good morning. It's October the 1st. Oh my God, it's already 1 month has passed. Right. So, we are still in chapter 4, discussing energy. So, most likely, today and then Tuesday. So, still 2 classes will be about this energy approach. And maybe by the end of Tuesday, we will start moving to chapter 5 about oscillations. So I realized in the morning that I need to post new homework, right? So there will be 2 homeworks about chapter 4, this chapter 4, right? Okay, I will take care of that after the class. And again, as I said, after this chapter there will be an exam, but it will be in the middle of October, so at least a couple of weeks we still have, right? So right now you don't have to worry about that. Okay, so back to the class and where we were. We've been talking about the potential energy, right? Which naturally appears if you start playing with the work kinetic energy principle, with the work side of the work kinetic energy principle. And so we defined potential energy. Then we restated conditions which a force must satisfy in order to be conservative. Right. So now, if you want to convince yourself that a certain force is a conservative force, you just need to take a curl, and if the curl is 0, then that force is conservative. And of course, if it's a function of position only. Then we define potential energy, right, in this way. So it's a negative work done as you move the system from the reference point to the point where you want to know your potential energy. And also then we sort of wrote the formula how we can find a force if, for example, potential energy is given. So you just take a negative gradient and that will give you the force. And then, so we decided to practice all these 3 points, right? So how to check that the force is conservative. Then the next logical step, how can we calculate the potential energy? And the next step will be how can we check how can we get the force out of the potential energy? Okay, so, and we started looking at the force of gravity, universal law of gravity, right? And somewhere Newton's name is also there, universal Newton's law of gravity, or whatever it is. All right, and so, of course, we simplified. We hid all the constants. So gamma, it's a minus g, m capital, m small, right? Interaction of 2 particles, m capital and m small. So first we proved that the force is conservative. We looked at the curl, and then we started calculating or deriving the formula for the potential energy. Right? So that's the definition, and that's the system, m capital, m small. So we want to find the potential energy at that point, right? And so reference point, universal freedom, you can pick any reference point you want. So we started with an arbitrary reference point, which is over here, R0. Right. And so now force is conservative. We could use any path we want because the work is path independent, right? So this is path independent. So we decided to choose the best possible path, right? Instead of going straight, sometimes straight is not the best option. Right, in this case, the best option, first you move radially, right? And then you move around the circle centered on the m capital, right? And so that's what I wrote down. We discussed that in the previous class, right? So minus, and I labeled reference point A, this B, turning point, and then C, a point where we want to find the potential energy. So we split, of course, integral into 2 parts, A, B, right? And negative, instead of force, we use that. This. Probably you know what, let me frame this because I will need it from time to time, and very often I have to just scan the whiteboard searching for that formula, right? And so we used it over here, right? And we ended up with these 2 integrals, right? And the last piece which we wrote in the previous class, we looked at this part, BC. dr infinitesimally small displacement. This is our trajectory, so dr is tangent to the circle. And r defines position of dr. So r is radial, right? So dr and r prime, they are perpendicular to each other. So as a result, dot product is 0. So that was the last point which I mentioned in the previous class. So this integral is 0. So now we need to take care of this integral over AB. Right, and of course in that integral, let me use probably different color. Right? So in that integral, no, dr, it's this. Right, so this will be our, okay, dr prime, since we decided to use prime to distinguish it from the upper limit. The upper limit here is r. Okay, so that's dr, and what is r prime? R prime, it's this now, right? So in this case, this is our r prime. So dr, that way, r prime from m capital to the point where dr is. So they are parallel to each other. So the angle between them is 0. Dot product is just a product of their magnitudes, right? Okay, so let me write it. So in this case, r prime is parallel to the r prime. So, and of course, that integral is not 0. So we will get minus, okay, gamma I can take outside. And now what we have, r prime and that r prime gets cancelled. So we will have dr prime over r prime squared. Right? So this r prime and that r prime, because now it's will be a product of two magnitudes. One r prime can be cancelled. And so now, since it's an integral over r, we can write it's from r naught to r, from this to that point. Okay, so that is integral of that will be minus 1 over r. If we differentiate, we will get plus r squared, yeah. So it will be minus gamma minus 1 over r prime from r naught to r. Right, and as a result, we're getting gamma over r minus gamma over r naught. So that's our potential energy, right? And nothing wrong with this potential energy, right? But nothing wrong, it doesn't mean it's the best, right? Who wants to, here gamma it's a constant, r naught also, a reference point, r naught is some constant number, right? Who wants to drag this constant all the time if it doesn't, if it's not going to do anything in your calculations, right? So it's just extra wasting ink, wasting space on the whiteboard. So let's try to pick the best possible point for the reference point. And so we just want to get rid of this term. So if you dragged r naught, the reference point, to infinity, of course this term is 0, and we can simplify the expression for the potential energy, right? Again, we're not changing anything significant, right? So just to simplify, or to make it, yeah, let's write to simplify. R naught goes to infinity, the reference point, and as a result, gamma over r naught goes to 0. So as a result, potential energy U at r equals to gamma over r. And so now we can recall gamma. So it will be minus g m capital M small over r. So that's our potential energy. Right. Let me frame it. And you know what, in general, if you have a finite system, finite in space, right, in size, like a set of masses, for example, right, finite in space, or a set of charges, again, finite in space, right? I started thinking, which course I'm teaching right now? Is it EMAC or classical mechanics, right? Because physics 2 and now classical mechanics, right? So sometimes I need to realize which course is this one. Right. So if you have system finite in size, the most convenient reference point is at infinity all the time. Again, to make this constant, to disappear this constant, to make this constant disappear. Right. But of course, for example, you can ask, but how about a capacitor? Of course, in a mag, right? So not classical mechanical system. So how about a capacitor? For example, a parallel plate capacitor, a PP capacitor, right? If I abbreviate it. How come that in a parallel plate capacitor the reference point is not at infinity? Usually, you remember, the reference point is at the negative electrode. How come? Because it looks like a capacitor, it's a finite system, right? How come that this system doesn't follow this trend? If the system is finite in size, the most convenient point is at infinity. And the answer is, strictly speaking, from the mathematical point, how we introduce a parallel plate capacitor. It's an arrangement of two infinitely large charged surfaces. So infinitely large, it means that it goes to that infinity, it goes to that infinity. So strictly speaking, from the mathematical point of view, a parallel plate capacitor is not a finite system, right? It's an infinite system. And in that case, of course, you will pick the best possible reference point for that particular case. And for a parallel plate capacitor, the best point, nothing can be better than at the negative plate. But again, if you have a finite system, then the best point is at the infinity, at infinity. Okay. So now, we derived the potential energy, and now let's check, can we get from here, from this U, that force? Okay. And of course, we have the formula. And as I said, very similar problem will be in your homework. So that was 1, 2, and now option 3. So let's check it. So basically, we need to get F if you take a gradient of U. Or I will just take gradient of U, and of course I will get negative F. Right? So let's look at the X component. No, it's on. Right, so curl, not curl, gradient of U, X component. Right. So of course it will be d over dx out of U. This is U, so it will be minus gamma m. And okay, let me write R again in terms of components. So it will be x squared plus y squared plus z squared and to the power of 1 over 2, right? Okay, if we differentiate this, okay, constants, they don't care about our differentiation. Minus 1 over 2 appears. Where should I write it? Okay, maybe here, 1 over 2, right? Then we differentiate x squared, it will be 2x. And downstairs we will have power of 3 over 2. Right, so it will be r to the power of 3. Okay, I will squeeze it back to r. Right. And so 2 goes, minuses goes, and we will get gmm r to the power of 3x. Right, which is minus over here, so it's a minus x component of the force. So minus f x. And so you can do the same with the y component, z component. Yeah, so from this potential, we're getting 3 components of the force. Right. So, and similar I can write so. Similar, of course, we can get that the gradient, it's difficult to write here at the bottom. And at the same time, I don't want to start over there. Right. So y equals to minus fy and gradient of u z equals to minus f sub z. Okay, so we went through all the tools. We applied all the tools which we've introduced in the previous class, right? And as I said, in your homework, you will have something similar where you have to do exactly the same. Check if the force is conservative, find potential energy, and then check if what you got makes sense. Right. So, at this point, we can say, yeah, this box of tools, energy tools, now is full, right? So we've developed all the energy tools that we need in order to analyze behavior of the system, classical systems, right? So now what? Now we have to apply them, and we will start applying them for one-dimensional system. Right? And we will have to slightly adjust them, basically simplify for one-dimensional case, and then we will look closer to the end. We will start looking at one example. Right. Okay, but first we need to say which one-dimensional system, a few words about one-dimensional systems. Okay, so the next will be one-dimensional systems. So, and so the goal is, let's just adjust these tools, energy tools, and apply them for 1D systems. Right? Let's adjust and apply our energy tools for a one-dimensional system as the simplest system for 1D systems. That's the whole idea now of this class and probably the next one as well. So one-dimensional system, it's a system which needs only one parameter to be described completely. So using one parameter, you can describe position of the system, dynamics of the system. Pretty much if you know that, you can find everything. If you know that one parameter is needed in order to describe the system completely, right? And we're going to look at two types of one-dimensional systems. First one is the linear one, when an object is simplest possible, right? So when an object moves along a straight line, like a train on a railroad track, right? And the second, okay, let me write it first. So let's say, so we have 1D systems and two options, right? So first one, a linear one, a linear system. Yeah, maybe I will draw something like, so let's say we have X and some object travels, right? And the second one, the second system is, okay, if this is linear, then of course the next one is a curve linear. It's sort of like a roller coaster track. In that case, okay, in this case, yeah, you can introduce only, since it's a motion along along a straight line, right? So yeah, obviously you can introduce X and it's enough. But if you have a curve linear system, like a roller coaster track, so if you look at that, so strictly speaking, all coordinates changes, right? X, Y, and Z, because cart moves right, left, up and down, right, and even forward, and even sometimes back. Right, so it looks like everything is changing, but because there are tons, okay, not tons, of plenty of forces of constraints, because the cart is attached to some track, right? As a result, there are plenty of normal forces, for example. So as a result, we should be able to introduce only one parameter. And using that parameter, we should be able to find everything x, y, and z. So it means it's still one-dimensional system, because one parameter is enough to describe this behavior of this curvilinear system. For example, that parameter can be just a distance along the track, right? S. But it's still one-dimensional system. And because of the forces of constraints make that system one-dimensional. All right, curvilinear system. Okay, roller coaster. Or a bead on on some wire. All right. Okay, let me draw some. For example, this, right? And so that's some track. And it's one-dimensional if you introduce this, for example, parameter. Let's say the card or the bead is at this point, and if you measure just this distance s from the beginning, okay, so that can be used as a parameter. Okay, so first we will start with linear systems, right? Again, as I said, we will adjust our tools, apply, and then for curvilinear, there's like a section where Taylor goes into adjustment of the tools for curvilinear system. For several years I covered them. Then at some point I stopped it. I don't like how it is. There is no smoothness, kind of very. Eventually I just dump it and I will just write something very simple, right, in order to avoid wasting time doing that, making those adjustments. So anyway, let's start with linear system, all right? And curvilinear, I will just say, so exactly the same things can be applied for curvilinear, right? So let's start with a linear one. A linear system. So first of all, let's adjust the expression for work, right? And then we're going to state 3 remarkable features of one-dimensional systems. And then we're going to use, when we start looking at examples, all of those remarkable features, not all, some of them will be used. So the first of all, work, let's just adjust slightly. Right, so adjust, and then we'll start applying. So first adjustment. Right, so of course, in general, you know what? It's time to change the marker. So work equal, oops. Okay, I hope it will start working. F dot dr. I hope it will start working better. It's brand new. I just took it from the department. All right. So it's a 3-dimensional case, but for one-dimensional situation, right? So what? What about the force acting in the y direction or z direction? They act perpendicular to the displacement along x direction only, right? So as a result, work done by the y component of the force, work done by the z component of the force will be 0, right? So as a result, this can be reduced to the integral of fx dx, right? So I will just write, so fy and fz are perpendicular to dx, and it's a sign of perpendicularity, right? They don't do work. So as a result, work, of course, can be written as an integral of fx dx, right? And now the rest will be about conservative forces for one-dimensional system. First, let's revisit those two conditions that a force must satisfy to be called conservative, because those conditions again will be simplified significantly, right? So, it was first we just slightly changed the work, and now conditions. Okay, let me write. Let's revisit conditions. Or let's adjust. Let's adjust conditions for F to be conservative. So you remember, first one, the force must be a function of position only, and the second, work is path independent. Right. So first one, F is a function of position. Okay. Which way I wrote? Just a second. Yeah, in this case it will be F is a function of a position only, one-dimensional case. We assume it moves along the x-axis. One dimension function of a position only. And the second, right, of course, work is path independent. Okay, so let's look at the second statement closer. And first, you know what? Probably first I write adjustment. Right? First I write this first remarkable feature, and then we will prove it. So basically, the first remarkable feature for one-dimensional system is if the first condition is satisfied, if the force is a function of position only, then the second condition is automatically satisfied. So if 1 is true, then 2 is guaranteed. So that's the first remarkable feature. So it's now in the, let's say the system is exposed to the force just constant, like mg. We will see it in maybe in 15-20 minutes. Mg, it doesn't depend on the position. It's just basically the special case of a dependence on x, right? So if that is true, then the second, we can tell immediately that the work is path independent and the force will be conservative. Okay, so let me write this. The first remarkable feature, right, the first, and as I said, there will be 3 of these remarkable features. The first remarkable feature of course, it's only true for one-dimensional system. Remarkable feature for a linear one-dimensional system is that the first condition guarantees the second one. Is that the first condition which we wrote, okay. Guarantees the second one. So in this case, we don't have to check both. Check the first one, and if it's true, then your force is a conservative one. Okay, let's prove it. Right. And now I'm thinking, will I be able to squeeze it? Okay, probably I will try. So let's assume that we have system which lives on this line, on this straight line. Call it x. And all right, so we need to show proof that the work done by the force between points, let's say A and B, is path independent, right? So instead of going directly from A to B, let's just go somewhere. Let's go to Alaska first and then come back to the point where we want to be, right? And let's calculate the work done over that more complicated, over that or slightly more complicated path. So let me introduce point C, right? And so first I will calculate the work if I go from A to C and then only to B. So not directly, but through some arbitrary point. Right. So I will go first from A to C and then from B to C. Right? Let's calculate this work. So work, which way I label it? Okay, so A, C, B. Of course, the work is just an integral, so we can split it into as many integrals we want. It's one-dimensional plus integral, right? That's why we started with adjusting the expression for an integral. Right? And so, of course, we can split it into work done from A to C first, and then plus work done to move back from C to B. But again, it's just a one-dimensional integral. We can split WAC into two parts. So the first one, WAB, and of course WBC, right? So we can split this into two. So it will be WAB plus WBC and WCB from the first split. And of course, the last two terms, WBC and WCB, it's the same integral, but in opposite directions. So it will be, this will be a positive, let's say, positive integral, and that will be negative integral of the same integral, right? So of course, that the last two terms, they cancel each other, right? So this is equal to negative WCB, right, for example. So as a result, this gets cancelled, and we have just a work done between A and B. And again, so let me finish this. And of course, since we picked point C arbitrary, it's completely arbitrary point. So of course, we can position here, there, or you can make, I don't know, two additional stops. You can stop at C, and then maybe then you can stop at D, and then come back. And every time, all those parts, additional parts, will be covered twice, calculating work on the way there and on the way back. And every time, those two terms are going to be of the same, will have the same value, but opposite in sign. One is positive, the other one is negative, canceling each other every time, except for the work between 2 points, your initial point and your final point. So it doesn't matter how complicated your path is for one-dimensional case, the work will be path independent. The work is path independent. Right, so work is path independent. And again, in this case, we didn't use anything except for the fact that the force is a function of position only. Right. Okay, so the first remarkable feature is here. Okay, maybe I should size it. Whenever I pronounce remarkable, it reminds me that movie, The Producers, the new one, right, with Matthew Broderick, I think, right, and that the worst director ever lived, right, when they were sort of discussing that play, right, and he said it's remarkable, right. I never realized that the Third Reich was in Germany, right. Right. And the way he pronounced it, remarkable. Right? It was so juicy, right? I still remember that. Okay, so remarkable feature number 1. Now let's talk about the second remarkable feature. And now I have to move to this side. The second remarkable feature. So now we know how to calculate work, how to check if the force is conservative, right? And now let's say we check the force is conservative. We calculated the potential energy of a system, and now we want to analyze behavior of the system. And now we can use the second remarkable feature to analyze behavior of the system in this way. So if you plot potential energy versus position of the system, U versus X, then you can analyze that curve sort of like a roller coaster track to analyze behavior of the system quantitatively. Right. So it helps to visualize qualitatively. Yeah. Right. So that's the second. And again, when we look at the example, I will also plot for that particular system. I will plot U versus X, and then when you have that plot, it's much easier to see what system is going to do, sort of very quickly. Right? But of course, if you want to get into the details, right, of course, you will have to go through calculus, which you know. All right, so let me erase this. And after that, there will be the third remarkable feature. And then, of course, example where we will use some of them. So I use blue. Okay, so let me. So the second remarkable feature. The second. And again, it's true only for one-dimensional systems. Okay, let me write underneath. So a plot U versus X helps to visualize behavior of the system. Helps to visualize the behavior of the system. Okay, a system. Of course, one-dimensional system. Okay, so that's the second remarkable feature, right? And let's look at one example. Okay, some completely arbitrary situation. Of course, we assume that force is conservative, so we can introduce potential energy, and let's say potential energy, and we plotted the potential energy. So I just want to estimate the amount of space I might need. So let's say this is U. This is X. And some arbitrary plot. Let's say, how many peaks? 2. Right, so let me. Right. Completely arbitrary situation. Right. So of course, we can get information about the forces easily, right? So for one-dimensional case, Fx will be equal to what? Minus x hat du over dx. du over dx. So I switched from partial derivative to straight derivative for one-dimensional case. Right. Okay, it's a vector we can put. Right, so now if, for example, you look at this point, which way I label it, it doesn't matter. I didn't label it. So the slope du over dx is positive, minus in front, so the force is going to be negative. Negative vector, what does it mean? It means that it points in the negative x direction. So of course force acts this way. Then if you take, for example, this point, of course now the slope is negative, but minus in front, so the force is positive. And when the system is on this part of the curve, at this point, so the force acts to the right. And the same here, right? This will be the force, direction of the force here, direction of the force will be that way. And of course we also immediately see the stationary points, right? So let me label them. So let's say this is what, x1? Yeah, x1, right? So x1 is a stationary point, it's maximum, right? This is x2, again stationary point and minimum. Right? So let me write something about this. So x1, which we wrote, and x2 are stationary points. And of course, you know from calculus how we can find them. Just first derivative of the function must be equal to 0. Right? So it's du over dx at those points, x1, x2, must be equal to 0. Right? We're going to use it, of course. And of course, you know, we're just refreshing it. And of course, for the maximum derivative, second derivative of the function must be negative, right? And for the minimum, it must be positive. Right. So which way I wrote it? Just immediately. Second derivative of u with respect to x. Right. At x1, it's if it's less than 0, then it's a maximum point, and of course the system over there is going to be unstable, right? So it's a maximum, and the system is unstable. Let me write underneath. So the system is unstable. Right, unstable. And of course, what does it mean unstable? If you slightly displace the system from the stationary point, in this case, this force immediately will drag the system away from the stationary point. It's not going to return. And if you displace it in this way, this force, again, will drag the system away from the stationary point, and the system will never come back, right, by itself. Right? So it's unstable. Right? And now the second. So if the second derivative of the function with respect to x2 is positive, then of course this is the minimum point, and the system is stable. Is stable for small disturbances, right? Oops. Yeah, marker started working better. It needs to be warmed up, right? Yeah. So if you displace it slightly to this point, okay, so we have a restoring force which tries to bring the system back to the stationary point. And of course, if you displace it over there, this force will try to push it back gently to return it to the stationary point. And again, we will use this in our example. Let me check what else needs to be mentioned. Okay, I'm not going to write about the forces, you know that. And of course, you can use conservation of mechanical energy, for example, to, again, quickly understand what happens with the system, right? For example, okay, let me write conservation of mechanical energy can be used. Mechanical energy can be used. So which is, let's write in this way, delta K equals to minus delta U, right, in this form. And we can look, for example, over this stretch. As the system, for example, moves this way from this point to the stationary point. So what happens with delta U? As you move, delta U increases, right? So delta U is positive. As you move this way, delta U increases, and so if delta U increases, then delta K, so it's positive. Then delta K is negative. Delta K is negative, it means kinetic energy is going down, right? So it makes sense. It's like in a roller coaster, the car climbing, potential energy goes up. As a result, kinetic energy is going down, right? So delta K is negative, right? So the system is slowing down. And of course, if you look over this stretch, of course, now potential energy is going down. So delta U is negative. Delta U is negative. And of course, as a result, delta U is negative, and this minus in front, delta K is positive. So system kind of is speeding up, gaining kinetic energy, right? So as a result, delta K is positive. So the system is speeding up. And exactly the same over here. So analogy with roller coaster, lots of similarities, right? So you can imagine a roller coaster, and you can analyze behavior of any complicated one-dimensional system, right? If you can plot this, right? So it's useful, right? If you again want to see quickly the behavior of the system, and again, when we look at the example, you will see that it's useful. It can be useful. All right, so let me check if I mentioned everything. And of course, if you can imagine, if you provided to a system a certain amount of total mechanical energy, right? If that mechanical energy is somewhere at this level and the system is in this range, right? So then the system will be sort of confined. It will be like in this potential well without being able to move. But if you keep increasing the total mechanical energy, and if your mechanical energy is somewhere on this level, then of course it will allow the system to escape to that side, to that infinity, right? But of course it will never be able to escape on this side, to this side. And of course if you provide enough of total mechanical energy, then of course the system basically is free, so throughout the whole range. But of course it will be slowing down slightly over here, then again speeding up, then again slowing down over that peak. Right? Okay, so all that stuff which you used in physics 1. Okay, so that's the second remarkable feature. Again, the first one, the second condition. If the first condition is satisfied, the second is automatically satisfied. Second condition, the second feature the second helps to analyze the behavior of the system. And the last one, the third remarkable feature, is this. In the previous example, you remember when we sort of juxtaposed Newtonian approach, approach using Newton's second law and energy approach. You remember what was the major difference? That Newton's second law allows us to get the function, right? How whatever parameter changes with time. But the energy approach kind of easier, but it allows us to find a value of some quantity at a particular point. So you're not getting the function. You're not getting a complete solution of the system, complete solution, right? So it's true almost all the time except for one-dimensional system, linear one-dimensional system. So if you have one-dimensional system, even using energy approach, you can get a complete solution. So you can get a function. Let's get that. Let's look at the example, right? But again, it's only true for one-dimensional system. So now, what should I erase? I guess that part. So to write the third remarkable feature. Okay, I use the blue color, yeah. So, which way I wrote the third remarkable feature? Conservation of energy can lead to a complete solution of the motion, right? Okay. The third remarkable feature. Conservation of energy. Okay, mechanical energy. Conservation of mechanical energy. Can lead to a complete solution of the motion. Complete solution of the motion. Basically a function, so we can get a function complete solution of the motion. So, and let's show how it's done. So let's start with total mechanical energy. Of course, E equals, again, which T or K we used? T. T plus U. In physics 1, in physics 2 and physics 1 we used, I think, K, so that's why sometimes. And we assume there are no losses, right? And total mechanical energy is a constant, so you can find it at any moment of time, right? So we assume that E is given. Right? And so, of course, we solve it for T. It's 1 over 2 mx dot squared, one-dimensional system. So not just V x dot we can use. And it is equal E minus U. I'm not writing U explicitly because it depends on the system which U. All right, so x dot equals square root of 2 over m E minus U. Of course, U is a function of x, and of course it's a dx over dt. Of course, we can get, okay, let me write dx over dt over here. Dx over dt. So now, strictly speaking, you know what, also, now I realized, let me write over here, it's a function of x. First I thought it's kind of not important, but now I realize for the next step we need. So now we just need to separate variables, basically, right? Because this side is a function of x, so we need to combine with this dx, and dt should be moved to the other side, right? So it will be dx over square root of 2 over m E minus U, and it is equal to dt. So strictly speaking, we just separate variables. And now integrate because one side is the function of one variable and the other side function of one variable. Right, so it will be, which way I wrote it? Yeah, just in this way. So, and now after integration, of course, we will get t equals integral. I think I will take m over 2 outside of the integral. Yeah, let me write square root of m over 2 and integral of dx and square root of e minus u x, right? And it's from sum x naught to x. So if you integrate it, you will get a function. Right, let me frame it. And of course, then you will have to invert it, turn it inside out. Of course, after this, after the inversion, you will get, of course, x as a function of time. But again, it's true only for one-dimensional system. For many degrees of freedom, of course, it doesn't work. In order to get the equation of motion, of course, you will have to use Lagrangian formalism, Hamiltonian formalism. So, quick example, which is quite simple, and then there will be more complicated example. Tower. Well, what's the name of that guy who threw rocks from Pisa Tower? Timothy, yeah, I was just slipped off my mind. Okay, whatever. All right, so it's something similar, right? Somebody at the top of the tower, right, dropping rocks, or whatever, balls, right, with some vicious smile, right? So we need to get the equation of motion of that rock. So, and just as an example of application of this example. So, is it stone? Okay, rock, stone.
It's Galileo.
Galileo. Oh, I thought so, but I started doubting myself. Right? It happens. Right? Yeah. So a stone. Okay, dropped. So it means initial velocity is 0. A stone dropped from some tower. Right. Okay, so let me draw the tower. Looks like London Tower. Looks so scary, right? So, okay.
It's too bad you pursued physics instead of your art career path.
Yes, yes, I'm trying to combine it. Right. Okay, vicious smile didn't work well, but okay, I will work on that. Okay, and so what else is given? Nothing else, right? From rest at t equals 0. And so, one-dimensional system. So let's introduce coordinate system. So it will be x. I will position the origin at the place where the stone was originally, right? And what we need in this case, okay, so initial point is 0, final point, it will be some arbitrary point x, right? And so what else needs to be found? E. And expression for the potential energy. E, again, it's a constant. You can use any point, right, to find E. Right. So let's find E. Okay. Let me at t equals 0. So E at t equals 0. Of course, E is constant, but I want to find that constant at that moment of time. Right. So T, of course, is 0 plus potential energy, and now I realize that something is missing in order to use potential energy properly, right? So I need to show the reference level, right? So since it's up to me, I want to position it anywhere I want, so I will position my reference level at the point where the stone was at t equals 0. So that's my reference level. As a result, kinetic energy is 0, potential energy is 0, total mechanical energy is 0, right? So now we just need to write the function for the potential energy, right? So it will be U equals. Okay, potential energy, as I mentioned to you in the previous class, it doesn't care about your actual origin of your coordinate system. It only cares where you position your the reference level, and if an object above that level, potential energy is positive. If it's below that level, potential energy is negative. Reference level over here, so it means that the potential energy, since the stone is below, potential energy is going to be negative, so we need to put minus, so it will be minus mgx, jx. gx. Damn it. Again, it's the same. Right? I remember after my first semester teaching, I don't remember, Physics 1, I read my evaluations, right? And one student wrote, J is not equal to G, right? Okay, so now sometimes it's still, I mispronounce it, but I'm trying to control myself. Right? So it will be negative mg x, right? In this case, it's x. Okay, so now we just need to plug it and integrate this simple integral. So t equals square root of m over 2 and integral from 0 to x. Again, x is some arbitrary point. And dx and square root of minus plus mgx, right? Okay, it's trivial integral. Of course, you will end up with square root of 2x over g. You invert it, and of course, you will get that well-known part of a kinematic equation, right? So x equals gt squared over 2. So we got the function. Okay, that's the trivial example. Now, let me just write one sentence. Okay, I used to kind of cover this curvilinear one-dimensional system, transitions to curvilinear systems, and then never liked it. Kind of they're clumsy, everything, and it needs lots of work. At least I didn't like the way the book it is done in the book. So eventually I decided just to skip it. Because anyway, results are the same. So pretty much all these tools which we energy tools which we adjusted for one-dimensional system, linear one-dimensional system, can be used for a curvilinear system. Right. And after that, we will start looking at the example which I like. Right. Yeah, let me write it at the top. So that was this third remarkable feature. And so let me just write one sentence. All these energy tools for one-dimensional linear system can be applied to analyze curvilinear one-dimensional system. Okay. All these energy tools oops, not those tools. For one-dimensional system, for one-dimensional linear system. Can be applied to analyze curvilinear a curvilinear 1D system. Okay. Maybe at some point, if I rework that, I will continue discussing, but at some point, it's not the most important. Right. Okay, so now example. Okay, I used different props when I'm in the office. Now I couldn't find anything better than breadcrumbs as a cylinder and diamond box, just basically old Wi-Fi. Okay, so what do we have in this problem? Okay, so we have a cylinder. Okay, not cylinder, just a cylindrical surface. So the cylinder doesn't move, right? So it just basically like sort of grounded, right? So basically we have cylindrical surface. On top of that, there's a box. Cube, basically cube, right? Which rocks on at the top. So basically we need to analyze this system. Radius of the cylinder is given, the size of the box is to be given. So we need to analyze the stability of the system, the behavior of the system when it is at the top. And actually we'll see how many stationary points are, what's the feature or features of this stationary point or that stationary point. But of course at the end we will see that we'll have to analyze this stationary point when the center of mass of the cube is right above the center of the cylinder. So that's the system. And it's still one-dimensional system. But now analyzing this system is more complicated. Okay, so we'll get back to these props later. First, we need to draw the picture. Right? And in this picture, in this case, picture is very important. So maybe I can use this. Finally, I need lots of space. Yeah. You know what? First, I need to write an example. It's example 4.7. Sorry.
So essentially, we set our potential energy to 0 at some point, make lives easier.
Can you repeat it again? Because the voice was kind of up and down, and some words I missed.
Oh, okay. So we have like our potential energy, and we're setting a reference point, and we're able to set a reference point to 0 at some point, like we did in the example on the board right now. And you set it to where the ball starts. And so you can just do that for any linear system?
Any point, it's up to you. It's your universal freedom, basically. You can position your reference point anywhere you want, and no one will be able to tell you that you are wrong or you are right. It just, some points are better, some points are slightly worse, but not that significant. Except that, as I warned you in the previous class, don't attach the reference point to something which moves. Because I've seen in the past students, right, the object system is kind of complicated, right? So there are two parts, but it's still one-dimensional. And students will attach to some object, to the position of the object, which will next moment will be somewhere else. It's not very well-defined reference point. I usually attach it to something which is obviously will be there forever and ever. But again, you can position it anywhere you want. And again, it doesn't care where is your origin of your coordinate system. Right? So potential energy lives its own life, right? And it doesn't care about the origin. Right? It only cares where you position the reference point. Yeah, a reference point. In this case, reference level. Okay, so now let's assume that this is my cylinder. At least finally I can use this. All right. Or maybe I can. No, it's enough. All right. So let's say this is my center. And first I will draw a position of the cube when it is in the equilibrium. Right. So of course it will be over here. Okay, so this is the point of contact when the cylinder is in equilibrium. Okay, I will use dash lines in order to show this cube position of the cube in this situation. And then I will displace it. Okay, and now let's displace it. You know what? I need probably. Right. So let's assume now the new point of contact is here. So new point of contact will be here. Right. And so now I need to draw this. So now I'm trying to estimate, is it? Yeah, it should be good. It should be good. Right. In this problems pictures are very important, right? And it will be somewhere over there. Right. Okay, so displaced. Oh, now I can see when I looked at this screen, it is really distorted over here. Okay, better. So that's the system. And I want to analyze the behavior of this, right, using what we just introduced, right? And I want to write down the potential energy of the cube. So how can we find potential energy over cube? Cube is the rigid object, right? And potential energy, how can we find potential energy over a rigid object? You find position of the center of mass, create a fake particle with the total mass at the point of center of mass, and potential energy of that fake particle is the potential energy of the whole rigid object, right? I'm thinking maybe I will add to the homework to prove that. It's quite simple. I remember I did it once for physics 1, right? So basically, in order to write potential energy of this cube, we just need to keep track of the center of mass, where the center of mass point is. Right? Okay, so now let's find the center of mass. And also, you will see that it's a one-dimensional system because we will be able to write potential energy as a function of one parameter only. And of course, if it's a one-dimensional system, right, it doesn't mean that there is only one parameter. You can come up with different parameters, but of course, for example, here I will use angle theta, but maybe instead of angle theta, you can use some other angle phi, or maybe you can use some height, right, some distance, right? So you can come up with different parameters. But of course, all the time, it must be one. So which I'm going to use, it's this angle theta. So that's our single parameter, and that parameter can describe motion, position, behavior of this cube. Okay, so now it's a one-dimensional system. And actually, before we start continue drawing, right? So let's analyze all forces. Right? Let's analyze all forces acting. So, and also, what is given? We know that the radius of the cylinder is r. Okay, let me write what is given. So given, so r, and the size of the cube is 2b. So this size, it's a 2b, right? And the radius is r. Okay, forces. Which forces act on the cube? So mg, first one. Okay, let me just put a bullet. mg. One-dimensional system, force, which is constant. So it's a special case of a dependence on a single parameter. It's a remarkable feature number one. If force is a function of a position only, but in this case there is no dependence, it means it's a special case, right? So it means that the second condition, that the work done by this force is path independent. So immediately we can write, using the first remarkable feature, that this is a conservative force. Right. So let me write, so first remarkable feature. Oops. So it's a conservative force. So we can introduce potential energy, and of course we all know that. So it's a U equals mg. Okay, so I don't have here y's or anything, so let me just for now write h. Right? Although I don't like using h. Okay, but in this case, I will still use it. Then, second, of course, there must be friction, and there must be plenty of friction force on the cylinder so that this cube can rock from side to side. So there must be friction force. And of course, you know which friction force we have here. You remember we have static friction force, kinetic. Here we have static friction force because there is no any sliding, right? So the point of contact at any moment of time is stationary, right? So it means that since there is no displacement, work done by the friction force, in this case static friction force, is zero. So static friction force in this case doesn't play the energy game. So we're planning to use the energy approach, but friction force in this case doesn't care about our energy game. And what it does, friction force in this case is just a force of constraints. And we're going to use the constraints at some point. All right, so which way I wrote it? F, just static friction. Let me write F, static friction. So work done by static friction equals zero, right? No displacement. All right. So as a result, F does not play our energy game again. So we can forget about this friction force. Okay, let me write the last force, the next one, and the last one, and then we'll call it a day. I thought I will be able to at least draw geometry. So we'll continue this next class. So, and then of course there is a normal force. And the same like in the example which we discussed in the previous class. Normal force perpendicular, plus there's no displacement to any possible displacement, right? Perpendicular to any possible displacement, but since we don't have any displacement, normal force, again, work done by the normal force is zero. So as a result, again, it doesn't care about this. We can forget about this. So work done by the normal force is zero. So again, we can forget about that. Again, the role of the normal force, it's a force of constraints. It allows us, not us, it allows the cube to be on the surface of this cylinder. Friction force allows it to rock without sliding. So two forces of constraints. So we have to only analyze potential energy associated with gravitational potential energy, right? So, okay, from here, again, as I said, we just need to write the potential energy, and using potential energy, we should be able to analyze behavior of the system. Right? So next we will have to just find the center of mass and find the distance from the reference level, which I will pick to the position of the center of mass. And then we will play with that function. First using the second remarkable feature, and then of course we will calculate everything properly using calculus. Okay, that's it.